Cold silence stretches between the stars, and yet we measure it with clocks. That silence hides a hard limit, a number that governs every rocket we have ever built. If light itself needs a full year to cross a certain distance, what chance do we have? Tonight, we're going to explore a question that sounds almost childlike. How long would it take us to travel 1 light year? It's something that sounds simple, but is actually a doorway into the deepest rules of physics. A light year. You've probably heard the term in documentaries or classrooms. It rolls off the tongue as if it were just another mile marker on a cosmic highway. But here's what most people don't realize. When you truly grasp it, it changes how you see distance, time, and even your own lifetime. And by the end of this, you're going to understand why 1 light year is both closer than it feels and far more unreachable than we like to admit. Before we go any further, take a moment to subscribe if you value clear, grounded explorations like this. Now, let's dive in. Let's begin with something familiar. A car hums along a highway at 100 kilometers per hour. In 1 hour, it travels 100 kilometers. The logic is comforting. Speed multiplied by time equals distance. Now scale that up. A jet crosses an ocean in about 10 hours. The International Space Station circles Earth every 90 minutes at roughly 28,000 kilometers per hour. Faster still. But space changes the scale completely. A light year is the distance light travels in 1 year through empty space. Light moves at about 300,000 kilometers per second. In a single second, it could circle Earth more than 7 times. Pause on that. We know this speed not by guesswork, but by measurement. In the 19th century, physicists bounced light between mirrors and timed its return. Today, lasers fire across vacuum tubes while atomic clocks tick with astonishing precision, losing less than a second over millions of years. When the pulse returns, the delay reveals the speed. Again and again, the number holds. 300,000 kilometers per second. Multiply that by 60 seconds, then 60 minutes, then 24 hours, then 365 days. The result is about 9.5 trillion kilometers. That is 1 light year. It sounds abstract until we compare it. The distance from Earth to the Sun is about 150 million kilometers. Light covers that in just over 8 minutes. So when you see sunlight, you are seeing the Sun as it was 8 minutes ago. Already, distance and time are braided together. Now imagine stretching that 8-minute gap to a full year. That is the scale we are confronting. Inside a quiet laboratory, a small silver clock sits beneath a glass dome. Its face is simple, its ticking is steady. Nearby, a laser emits a faint pulse, and a low hum fills the room from cooling systems that keep the instrument stable. That clock and that laser are part of how we define the meter itself. Distance is no longer a metal bar in a vault. It is the distance light travels in a fraction of a second. Our rulers are made of time. This is where the mystery sharpens. If 1 light year equals 9.5 trillion kilometers, how long would it take us to cross it with our fastest machines? The fastest human-made object ever launched is the Parker Solar Probe. At its peak near the Sun, it has reached speeds above 600,000 kilometers per hour. That sounds enormous. It is. But compare it carefully. Light travels more than 1 billion kilometers in a single hour. Parker's top speed is a tiny fraction of that. If it could somehow aim straight toward a target 1 light year away and maintain its maximum speed, the journey would take over 6,000 years. 6,000 years. That number should unsettle you. Civilization itself is only about that old. The pyramids of Giza were built around 4,500 years ago. A probe launched at Parker's record speed would still not be halfway to its destination. Here is the implication. With current propulsion, 1 light year is not a mission, it is a multi-millennia commitment. And yet, we keep asking the question. Because 1 light year is not just any distance. The nearest star beyond our Sun, Proxima Centauri, is about 4.2 light years away. If we cannot cross 1, we cannot reach even our closest stellar neighbor within a human lifetime. So we test ideas, we build faster engines, we refine measurements, we send probes like Voyager 1, now more than 24 billion kilometers from Earth, and we track its faint radio whispers. Those signals take over 22 hours to reach us. We measure the delay precisely. Radiotelemetry tells us where it is and how fast it moves. There is no mystery in the math. The mystery is scale. Midway through our reasoning, we confront a new constraint. It is not just about speed, it is about energy. To double your speed, you do not merely double the fuel. The energy required rises steeply, and as you approach the speed of light, the energy required climbs toward infinity according to Einstein's equations. That should not be possible, and yet every particle accelerator on Earth confirms it. Protons pushed to near light speed demand enormous energy for tiny gains in velocity. Their mass, in a relativistic sense, resists further acceleration. The equations predict it, the detectors verify it. The universe enforces a limit, so our central mystery becomes clear and testable. Given the measured speed of light, the verified equations of relativity, and the demonstrated limits of propulsion, is there any physically plausible way for a human-made craft to cross 1 light-year in less than a human lifetime? We can calculate trajectories. We can estimate fuel mass. We can simulate impacts with interstellar dust. Each scenario yields numbers, not fantasies. Some ideas strain engineering, others strain physics itself. In a darkened control room, screens glow softly. A trajectory arc curves across a digital starfield. Engineers watch as simulations run, numbers updating in quiet rows. A distant ventilation fan whispers overhead. The arc never quite flattens into a straight, easy path. It bends under constraints we cannot switch off. 1 light-year waits ahead, indifferent. We stand at the edge of a planetary cradle, holding equations that describe the cosmos with stunning accuracy. Yet those same equations tell us that the gulf between stars is not merely large. It is structured by laws that do not negotiate. And this is only the beginning of the question. If our fastest probes need thousands of years, what would it truly take to shorten that span to decades? What would we have to change about our machines, our energy sources, perhaps even our understanding of space and time? The answer is not a single number. It is a chain of constraints. And to follow that chain, we have to look more closely at what a light year really means. Light leaves a star, crosses emptiness for years, and arrives as a whisper in our detectors. That whisper carries distance encoded as time. If we misunderstand that translation, every journey we imagine will be wrong. A light year is not a measure of time. It is a measure of distance defined by time. That distinction sounds subtle, but it changes everything. In precise terms, a light year is the distance light travels in 1 Julian year, which is 365.25 days, through vacuum at exactly 299,792,458 meters per second. That number is not approximate, it is defined. The speed of light in vacuum is fixed by definition in the International System of Units. A unit of distance is built from that speed. Imagine a ruler made not of wood or metal, but of seconds. 1 meter is defined as the distance light travels in 1 divided by 299,792,458 of a second. We flipped the relationship. Instead of measuring light with meters, we measure meters with light. Inside national standards laboratories, atomic clocks sit in temperature-controlled rooms. Their timing comes from the vibration frequency of cesium atoms. When electrons shift between energy levels, they emit radiation at an extremely stable frequency. We count those oscillations. Over 9 billion of them define 1 second. A soft electronic beep marks synchronization across continents. This is how we know. When a laser pulse travels down a vacuum tube and reflects back from a mirror, the round-trip time can be measured against those atomic oscillations. Divide distance by time and you recover the same constant speed. Every repetition, every refinement, converges on that value. But how do we know the distances to stars in the first place? Here the story widens. The most direct method is parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. It is like holding your thumb up and alternating which eye is open. Your thumb jumps relative to the wall. Measure that tiny angular shift, and simple geometry reveals the distance. 1 parsec is defined from that geometry. It is the distance at which a star would show a parallax angle of 1 arcsecond. 1 parsec equals about 3.26 light-years. When space telescopes like Gaia map billions of stars, they measure angles smaller than 1,000th of an arc-second. The data are processed through careful calibration. Instrument drift is modelled. Systematic errors are checked against known reference stars. Distance becomes a solved measurement problem within margins of error. Stand in a dark observatory dome. The slit opens with a low mechanical whir. A telescope tilts upward, its motors humming gently as it locks onto a target. On a screen, a star sharpens into a pinpoint. Over months, its position shifts by a fraction of a pixel. That shift, accumulated patiently, becomes a distance in light-years. For stars too distant for reliable parallax, we use standard candles. Certain types of stars, like Cepheid variables, brighten and dim in a regular cycle. The period of that cycle is tightly related to their intrinsic luminosity. Measure how bright they appear from Earth, compare that to how bright they truly are, and you infer distance through the inverse square law of light. Again, this is testable. Cepheid distances overlap with parallax distances for nearer examples. If the two methods agree within uncertainty, confidence grows. Later. Type 1. A supernovae serve as brighter standard candles across even larger spans. Their peak luminosity follows consistent patterns, allowing astronomers to extend the cosmic distance ladder. Here is the twist. When we measure very distant galaxies, we do not rely on parallax at all. We measure redshift. As the universe expands, light from distant galaxies is stretched to longer wavelengths. Spectrographs split incoming light into colours, revealing dark absorption lines from known elements. If those lines are shifted toward red, we can calculate how fast the galaxy is receding. Under the current cosmological model, recession speed relates to distance through the Hubble constant. Measure the redshift, apply the model, and distance follows. There are uncertainties and ongoing debates about the exact value of that constant. Different measurement methods yield slightly different numbers. That tension is real and under active study. But for nearby stars within a few thousand light-years, parallax remains the gold standard. Midway through our exploration, a new constraint appears. A light-year is straightforward in empty, static space. But space itself is not static on cosmic scales. Over millions and billions of years, expansion alters distances between galaxies. For 1 light-year within our Milky Way, expansion is negligible. Gravity binds our galaxy tightly enough that local distances remain stable. This means our earlier definition holds cleanly for interstellar travel. Yet even within the Milky Way, stars move. They orbit the galactic centre at hundreds of kilometres per second. Proxima Centauri is not standing still relative to us. Over tens of thousands of years, its position shifts measurably. Survey mapping projects chart these motions by tracking proper motion across the sky. Combine proper motion with radial velocity, measured via Doppler shift, and we reconstruct three-dimensional movement. Distance is not just a number, it is a moving target. Picture a vast digital map projected onto a curved screen. Points of light drift slowly across it as time is accelerated. A faint clicking sound marks each simulated year passing. The nearest stars trace gentle arcs, weaving a slow ballet around the galactic centre. Any spacecraft aimed today would need course corrections centuries later. So when we say 1 light-year, we mean a specific geometric distance measured under well-tested physical laws. We mean 9.5 trillion kilometres in vacuum. We mean a span confirmed by parallax angles, atomic clock timing, laser ranging, and spectral analysis. There is little ambiguity in that distance itself. The ambiguity lies in us. Because once we anchor the number, we must confront the ratio between that distance and our achievable speeds. If light needs 1 year, and our fastest probes move at a tiny fraction of light speed, the arithmetic becomes unforgiving. And arithmetic does not negotiate with ambition. Before we calculate travel times in detail, we have to understand the vehicles we would use. Chemical rockets, ion drives, gravity assists. Each has a measurable exhaust velocity. Each has limits grounded in thermodynamics and material strength. In a clean room lit by white panels, a rocket engine nozzle gleams under inspection lights. Engineers run simulations on nearby monitors. A faint hiss of compressed gas fills the space during a test pulse. The plume that will one day push a spacecraft outward is born from equations as rigid as the definition of a light year. The distance is firm. The laws are firm. Now we turn to the machines, and to the uncomfortable math that connects them to that single, stubborn unit of space. A faint radio signal crosses billions of kilometers and arrives as a pattern in static. That pattern tells us how fast our machines are really moving. When we compare that speed to the scale of a light year, optimism fades into arithmetic. So how fast are we, truly? We begin with Voyager 1. Launched in 1977, Voyager used chemical rockets to escape Earth, then gravity assists from Jupiter and Saturn to gain additional speed. Today, it travels at roughly 17 kilometers per second relative to the Sun. That number is not guessed. It is calculated from Doppler shifts in its radio transmissions. As the probe sends a carrier signal toward Earth, its frequency is slightly shifted by motion. Measure the shift precisely, and velocity follows. 17 kilometers per second sounds impressive. It is. But light moves at 300,000 kilometers per second. Voyager crawls at about 1/50,000th of light speed. At that pace, crossing 1 light year would take roughly 18,000 years. 18,000. That is longer than recorded human history. Inside a deep space network facility, massive dish antennas rotate slowly against the sky. Electric motors hum as they track a point too faint to see. In a control room, a green waveform flickers across a monitor. Each oscillation is Voyager's voice. The delay between transmission and reception grows by minutes each year. That delay is how we know its distance. Radio signal delay is our measuring tape across the solar system. Chemical rockets gave us Voyager. They work by expelling mass at high speed in the opposite direction. The exhaust velocity is limited by chemical bond energy. For typical liquid hydrogen and oxygen engines, exhaust velocities reach about 4.5 kilometers per second. That caps the efficiency. To go faster, you must carry exponentially more fuel. This is the rocket equation, derived by Konstantin Tsiolkovsky in the early 20th century. It links final velocity to exhaust velocity and the ratio of initial mass to final mass. The equation is simple. The consequences are brutal. To double your speed, you do not double your fuel, you increase it dramatically. There is no loophole here. Ion engines improve efficiency. Instead of chemical reactions, they use electric fields to accelerate ions to much higher exhaust velocities, sometimes above 30 kilometers per second. NASA's Dawn spacecraft use such engines to orbit 2 asteroids. Ion drives sip propellant slowly over years, building up speed gradually. But even ion engines remain far from relativistic. If an ion-driven craft could sustain a velocity of 50 kilometers per second, which is optimistic, crossing 1 light year would still require about 6,000 years. Gravity assists offer clever boosts. By flying close to a planet and stealing a tiny bit of its orbital momentum, a spacecraft can gain speed without burning extra fuel. Parker's solar probe used repeated flybys of Venus to reshape its orbit and fall closer to the Sun. Near perihelion, it reaches record speeds above 190 kilometers per second relative to the Sun. That is the fastest any human-made object has traveled. Yet even 190 kilometers per second is less than 1,000th of light speed. At that velocity, 1 light year would take over 1,500 years. Here is the uncomfortable pattern. Every method we currently use yields travel times measured in millennia. The differences between them matter for planetary missions. They barely dent interstellar scales. Midway through this reasoning, we hit a reframing constraint. It is not just about top speed, it is about sustained speed. Parker reaches its peak velocity only near the Sun, where gravity has accelerated it inward. It cannot maintain that speed in deep space without enormous propulsion. For interstellar travel, what matters is cruise velocity over decades or centuries. Sustained high velocity demands continuous thrust or an immense initial impulse. Both require energy and mass. Picture a test stand in a desert facility. A prototype engine fires briefly. A plume expands into the air with a sharp roar, then fades into a low rumble as it shuts down. Engineers examine readouts. Thrust is measured in newtons. Fuel flow in kilograms per second. none of the numbers approach what would be required for even a tenth of light speed. Let us quantify that threshold. 10% of light speed is about 30,000 kilometers per second. At that velocity, 1 light year could be crossed in 10 years, as measured in the rest frame of Earth. That sounds almost manageable, a human lifetime mission. But accelerating even a modest 1,000-ton spacecraft to that speed would require kinetic energy on the order of 4 times 10 to the 20th joules. That is comparable to the total energy consumption of human civilization over many years, and that figure ignores inefficiencies and the need to slow down at the destination. Energy is the wall we keep hitting. Nuclear thermal rockets, which heat propellant using a nuclear reactor, could double chemical exhaust velocities. Nuclear electric propulsion could power stronger ion drives. Both are under study, both improve performance incrementally. Neither comes close to relativistic cruise speeds. And so the pattern becomes clear, with chemical propulsion, ion drives, and gravity assists. 1 light year remains thousands to tens of thousands of years away. This is not pessimism. It is calculation grounded in telemetry, Doppler tracking, exhaust velocities, and energy budgets. Every parameter can be measured in a lab or observed in flight. In a dim operations room late at night, a clock on the wall ticks softly. A spacecraft status packet arrives after hours of travel. Engineers nod quietly. The numbers match predictions within fractions of a percent. Physics holds. The universe behaves. But that reliability is also the cage. If the speed of light is the ceiling, and our engines barely scratch a fraction of it, then crossing 1 light year within decades demands something fundamentally different. Not just better engineering, but a shift toward the edge of known physics. The next step in our journey forces us to confront that ceiling directly. Why can't we simply keep accelerating? Why does nature forbid us from matching light itself? To answer that, we have to stand face to face with relativity and with the experiments that prove it beyond reasonable doubt. In a particle accelerator, protons circle a ring at nearly the speed of light. Their energy climbs, their speed barely changes. That stubborn refusal is not a glitch. It is the universe enforcing a rule. So why can nothing with mass reach light speed? The answer lies in special relativity. In 1905, Albert Einstein proposed that the speed of light in vacuum is the same for all observers, regardless of their motion. That postulate sounds abstract. It is not. It has been tested for more than a century. Every high-precision experiment has confirmed it within measurable uncertainty. Here is the core consequence. As an object with mass accelerates toward light speed, its relativistic energy increases dramatically. The relationship is captured in a factor called gamma, which depends on velocity divided by the speed of light. As velocity approaches that limit, gamma rises steeply. Energy requirements soar. You can picture it like pushing a sled across ice that becomes thicker and heavier with each shove. Each extra gain in speed demands disproportionately more effort. This is not metaphor alone. At facilities like the Large Hadron Collider, particles are accelerated by electric fields inside long vacuum tubes. Superconducting magnets guide them in circles, as protons approach 99.999% of light speed. Adding more energy does not produce meaningful increases in velocity. Instead, it increases their momentum and effective relativistic mass. Detectors record collision products with extraordinary precision. The equations of relativity predict the outcomes. The data match. In a cavernous underground tunnel, magnets sit in a ring 27 kilometers around. A low, constant hum fills the air from cooling systems maintaining temperatures colder than deep space. Instrument panels glow softly. Within the vacuum pipe, invisible particles race, obeying equations written over a century ago. The speed limit is not theoretical whim, it is empirical. Atomic clocks flown on airplanes provide another confirmation. In experiments beginning in the 1970s, precise clocks were placed aboard jets and compared to synchronized clocks left on the ground. After the flights, tiny differences were measured. The airborne clocks ticked slightly slower due to their velocity and slightly faster due to altitude in Earth's gravitational field. The combined effect matched relativistic predictions. Time itself bends with motion. This matters for interstellar travel because if we try to push a spacecraft closer to light speed, we encounter two linked effects. First, from the perspective of observers on Earth, the ship's acceleration demands ever-increasing energy. Second, from the perspective of travelers on board, time would slow relative to Earth. That slowing is called time dilation. If a craft could reach 90% of light speed, gamma would be about 2.3. That means 1 year experienced on board would correspond to about 2.3 years passing on Earth. At 99% of light speed, gamma rises to about 7. The gap widens quickly. Here is the twist. From the traveller's frame, the distance to the destination also contracts. This is length contraction. A 1 light-year gap measured from Earth would appear shorter to someone moving at relativistic speed. In principle, this allows a traveller to cross vast distances within a personal lifetime, while centuries pass at home. It sounds like a loophole. Midway through this reasoning, we must apply the constraint. Even though time dilation and length contraction reduce subjective travel time, the energy required to reach such speeds remains enormous. Relativity does not offer a free shortcut. It offers symmetry. Observers disagree on time and length, but all agree on the invariant speed of light. To see how demanding this is, consider accelerating a spacecraft of modest mass to 99% of light speed. The kinetic energy required would be comparable to converting a significant fraction of the spacecraft's rest mass directly into energy, as described by E equals mc squared. For every kilogram, the rest energy equals about 9 times 10 to the 16 joules. Even tapping a small percentage of that would dwarf current global energy production. And we have no practical mechanism to convert mass to energy with perfect efficiency. In laboratories, matter-antimatter annihilation demonstrates the principle. When a particle meets its antiparticle, they convert into photons, releasing energy equal to their combined mass. We can create antimatter in particle accelerators. We can trap tiny amounts. But production is inefficient and costly. Storing meaningful quantities safely remains an unsolved engineering challenge. A containment chamber in a research facility glows faintly behind thick shielding. Magnetic fields hold charged particles in place within a vacuum. A soft beeping monitor tracks stability. The quantities are microscopic, enough to prove the equation, not enough to power a starship. Relativity imposes another subtle barrier. Even if we imagine infinite energy, reaching exactly light speed would require infinite energy. The equations diverge. Nature prevents the crossing. Particles with zero rest mass, like photons, travel at light speed. Particles with mass approach it asymptotically, never touching. This is the hard ceiling. So when we ask how long it would take to travel 1 light year, we are bound by 2 measurable facts. First, the distance is fixed by the defined speed of light and the duration of a year. Second, any craft with mass cannot reach or exceed that speed. Everything else is negotiation within those boundaries. We can choose lower cruise speeds and accept long travel times. We can aim for high fractions of light speed and accept staggering energy requirements. We can leverage time dilation to reduce onboard time while acknowledging that Earth ages faster, but we cannot ignore the limit itself. In a quiet classroom late at night, equations fill a chalkboard. The symbols curve across the surface in white arcs. Outside, wind brushes against the windows with a faint hiss. The mathematics look serene. Its implications are severe. The universe is not hostile, it is consistent. And consistency means that any serious proposal for crossing 1 light year must respect relativity not as a suggestion, but as a tested framework backed by particle accelerators, atomic clocks, laser interferometry, and a century of experimental scrutiny. If that ceiling cannot be broken, then the only path forward is to climb as close to it as we can. The question becomes practical now. What would it actually cost, in energy and engineering, to push a real spacecraft to a significant fraction of light speed? And where, exactly, does the wall become insurmountable? A spacecraft drifts in silence, and every extra meter per second it gains costs more than the last. The numbers escalate quietly, then violently. At some point, ambition collides with arithmetic. So where is that wall, exactly? To answer, we calculate energy. Kinetic energy in classical physics is 1/2 times mass times velocity squared. At low speeds, that works well. But as velocity approaches light speed, we must use the relativistic expression. Energy grows according to gamma minus 1 times mass times c squared. Gamma rises steeply as velocity nears the cosmic limit. Let us choose a modest spacecraft. Imagine a vessel with a mass of 1,000 tons. That is small compared to many proposed generation ships, yet far larger than current deep space probes. 1,000 tons equals 1 million kilograms. If we aim for 10% of light speed, about 30,000 kilometers per second, gamma is roughly 1.005. That seems gentle. Plugging into the equation yields kinetic energy around 4.5 times 10 to the 18 joules. That number deserves context. Human civilization currently consumes on the order of 6 times 10 to the 20 joules of energy per year, so accelerating this ship to 10% of light speed would require less than 1% of annual global energy output. Ignoring inefficiencies, that sounds almost attainable. But there are complications. First, rockets must carry fuel. The energy must come from somewhere on board or be delivered externally. If we rely on onboard fuel, the rocket equation returns with force. To accelerate to that speed and then decelerate at the destination, the required propellant mass would likely dwarf the payload. Second, 10% of light speed still means a 1 light-year journey would take 10 years in Earth's frame, plus acceleration and deceleration phases. That is manageable in principle, but only if we can sustain the energy flow and handle the structural stress. Now increase the target speed to 50% of light speed. Gamma becomes about 1.15. The required kinetic energy jumps to roughly 1 times 10 to the 22 joules. That is about 1/6 of annual global energy consumption for acceleration alone. Double it for braking. The curve steepens. At 90% of light speed, gamma is around 2.3. Kinetic energy for our 1,000-ton craft rises to roughly 1.2 times 10 to the 23 joules. That approaches the total annual energy use of humanity. And again, that is idealized. Real systems are inefficient. Engines waste energy as heat. Picture a massive power plant humming at night. Turbines spin with a deep mechanical thrum, steam condenses in cooling towers, multiply that by thousands. Even then, we struggle to supply the energy needed for a single relativistic launch. Here comes the mid-course reframe. Energy alone is not the only barrier. Power matters too. Power is energy delivered per unit time. If we want to accelerate to 10% of light speed within, say, 1 year, we must deliver that 4.5 times 10 to the 18 joules over 12 months. That corresponds to a continuous power output of about 140 gigawatts, comparable to the output of over 100 large nuclear reactors running constantly for a year, dedicated to a single spacecraft. And that assumes perfect transfer efficiency. Now consider thermal management. Engines converting energy into thrust will generate heat. In space, heat can only be shed by radiation. Radiators must glow and emit infrared energy. The hotter they run, the more efficiently they radiate, but materials have limits. Large radiator panels would extend like wings, vulnerable to micrometeoroids. In a design studio lit by cool blue screens, engineers rotate a 3-dimensional model of a starship. Thin radiator fins unfold from its sides. A faint hum from computers fills the room. The numbers scroll beside the model. Heat loads, stress tolerances, failure probabilities. Every parameter tightens constraints. Then there is fuel type. Chemical fuels are insufficient for relativistic travel. Nuclear fission offers higher energy density, but still falls short for sustained high acceleration of large masses. Nuclear fusion, which powers stars by fusing light nuclei into heavier ones, releases far more energy per kilogram. Experiments like tokamaks attempt to confine hot plasma with magnetic fields to achieve net energy gain. Progress is steady but incomplete. Fusion propulsion concepts, such as inertial confinement or magnetic confinement drives, could in theory provide higher exhaust velocities. If exhaust velocity approaches tens of thousands of kilometers per second, the rocket equation becomes less punishing. But sustained, controlled fusion in a compact spacecraft reactor remains an engineering challenge not yet solved. Antimatter offers the highest known energy density. When matter meets antimatter, nearly 100% of mass converts to energy. In principle, a few kilograms of antimatter could provide enormous thrust. In practice, producing even micrograms requires vast accelerator facilities, storage demands magnetic traps. A containment failure would be catastrophic. None of these statements are speculative. They follow from measured reaction energies, observed annihilation events, and demonstrated production efficiencies. There is another subtle barrier. Interstellar space is not perfectly empty. At high velocities, even sparse hydrogen atoms become a stream of high-energy particles striking the hull. At 10% of light speed, impacts resemble intense radiation. At higher fractions, they become more severe. Shielding adds mass. More mass demands more energy. The feedback loop tightens. Stand inside a materials testing lab. A beamline fires ions at a metal sample. The chamber vibrates faintly. Microscopic damage accumulates on the surface. Researchers examine it under magnification. Multiply that exposure by years at relativistic speed, and structural integrity becomes a central concern. So the wall is not a single brick. It is layered. Energy supply, power delivery, fuel mass, thermal control, radiation shielding, structural stress. Every layer compounds the difficulty. And yet, none of this says impossible. It says constrained. If we aim for 10% of light speed with a carefully designed fusion or beamed energy system, the energy requirements are enormous but not beyond the total capacity of a technologically advanced civilization over time. The question shifts from physics to infrastructure. Can we build and sustain such power systems? Can we dedicate them to a single mission? 1 light-year remains the benchmark. At 10% of the light speed, 10 years of travel. At 20%, 5 years. The numbers scale inversely with velocity, but the energy scales far more steeply. The universe offers a bargain. Faster journeys cost disproportionately more. In the darkness beyond the heliosphere, a probe continues outward at a steady pace. Its radio signal grows fainter. A soft hiss fills the background of receivers. The data confirm its velocity, unromantic and precise. We are creatures of chemical fire trying to step into a realm governed by nuclear and relativistic scales. If onboard energy is the limiting factor, perhaps the answer lies elsewhere. Perhaps we do not carry all the energy with us. Perhaps we let the sun, or distant lasers, push us instead. To explore that possibility, we turn to propulsion concepts that separate the ship from its fuel, and in doing so, challenge our intuition about what a spacecraft even is. A thin sheet catches sunlight and begins to move. No flame, no roar, just pressure from photons. It sounds fragile, almost poetic. Yet it may be one of the few propulsion methods that can scale toward interstellar speeds without carrying mountains of fuel. So can light itself push us across a light year? This is the idea behind light sails. Photons have no rest mass, but they carry momentum. When they strike a reflective surface, they transfer a tiny push. The force is minuscule at everyday scales. On a square meter near Earth, sunlight exerts only about 9 micronewtons of pressure. That is less than the weight of a paperclip. But space is patient. If a sail is extremely light and extremely large, and if it experiences that gentle push continuously, it can accelerate steadily without expelling propellant. The Japanese spacecraft Icaros demonstrated solar sailing in 2010. It deployed a thin reflective membrane and used sunlight to adjust its trajectory. The effect was small but measurable. We know it works because we measured trajectory deviations precisely. Laser ranging and radio Doppler tracking revealed slight accelerations consistent with photon pressure. The data matched predictions within error bars. To reach meaningful fractions of light speed, however, sunlight alone is insufficient. The intensity drops with distance from the sun, following the inverse square law. Beyond a few astronomical units, pressure weakens rapidly. Here the concept evolves. Instead of relying on natural sunlight, we could use powerful ground-based lasers to illuminate a sail. This is the foundation of proposals like breakthrough starshot. The idea is to build a phased array of lasers that focus coherent light onto a small, lightweight sail attached to a gram-scale payload. The beam would accelerate the craft to perhaps 20% of light speed within minutes. 20% is significant. At that velocity, 1 light-year could be crossed in 5 years, as measured from Earth, Proxima Centauri, at 4.2 light-years, would take just over 20 years for the signal of arrival to return. The physics of radiation pressure is straightforward. The challenge is engineering. To accelerate even a gram-scale craft to 20% of light speed in minutes requires laser power on the order of tens of gigawatts, concentrated precisely and sustained. The sail must withstand intense heating without tearing or melting. In a desert array at dusk, thousands of laser emitters align in silent coordination. Cooling systems hum with a low, steady tone. A wafer-thin sail, no larger than a dining table, waits in the beam path. For a few minutes, light does the work of rockets. The concept is grounded in measurable quantities. Laser power is measured in watts. Momentum transfer follows from photon energy divided by the speed of light. Thermal loads can be simulated and tested in labs with high-intensity beams. But there is a reframe here. Such laser-driven sails work best for very small payloads. Scaling the concept to a 1,000-ton crewed vessel would require laser arrays orders of magnitude more powerful and sails spanning kilometers. The infrastructure cost and precision alignment become staggering. Even minor beam divergence over millions of kilometers reduces efficiency. And then there is deceleration. A laser can push from behind, but slowing down at the destination requires either carrying additional systems or using the light from the target star, which may not be sufficient. Some proposals suggest magnetic sails that interact with the interstellar medium or stellar winds to break gradually. These ideas are under study but remain unproven at scale. Fusion propulsion presents another path. In theory, fusion reactions like deuterium-helium-3 produce high-energy charged particles that can be directed by magnetic fields to produce thrust. Exhaust velocities could reach tens of thousands of kilometers per second. That reduces required fuel mass compared to chemical rockets. Experimental fusion reactors on Earth, such as tokamaks and stellarators, confine plasma at temperatures hotter than the Sun's core. Diagnostics measure neutron flux, plasma density, and confinement time. Despite progress, sustained net positive energy output remains a work in progress. Translating that into a compact, reliable spacecraft engine adds layers of complexity. Antimatter rockets push even further. If matter and antimatter annihilate, the resulting gamma rays and particle jets could, in principle, provide extremely high exhaust velocities. The energy density is unmatched. But production rates are tiny. Particle accelerators produce antimatter inefficiently. Storage requires electromagnetic traps in ultra-high vacuum. A containment failure would release immense energy instantly. Current technology stores antimatter in nanogram quantities. Interstellar travel would require vastly more. In a high-security lab, a small magnetic bottle glows faintly within shielding. Instruments emit a soft periodic tone. The trapped particles exist for moments before annihilating. The scale is microscopic. The dream is not. Each advanced propulsion method shares a common theme. They are consistent with known physics. They do not violate relativity. They aim to approach significant fractions of light speed by increasing exhaust velocity or outsourcing energy delivery. Yet each faces engineering limits, material constraints, and cost barriers that grow rapidly with scale. 1 light-year remains the benchmark. If we could accelerate a lightweight probe to 20% of light speed using a beamed laser sail, the journey would take 5 years in Earth's frame. That is transformative for robotic exploration. For crewed missions, the mass problem reasserts itself. Midway through this analysis, the constraint sharpens. Even if propulsion is solved, interstellar space itself becomes an active hazard at these speeds. A dust grain no larger than a grain of sand, encountered at 20% of light speed, carries kinetic energy comparable to a small explosive. Shielding must be robust. Robust shielding adds mass. Mass demands more energy. The loop returns. In a simulation chamber, a stream of microparticles impacts a composite panel. Each strike produces a tiny flash and a sharp, ticking sound against sensors. Engineers analyze crater patterns. At relativistic speeds, the stakes rise dramatically. So we stand at a crossroads. Beamed sails may open the door to fast, lightweight probes crossing light-year distances within decades. Fusion and antimatter promise higher thrust but demand breakthroughs. chemical and ion drives remain bound to millennia. The question narrows: suppose we do solve propulsion for a probe? Suppose we reach 10 or 20% of light speed? What exactly are we flying through for those years? Interstellar space is not empty, it is sparse, but at extreme velocity, sparse becomes significant. To understand whether one light year is merely distant or actively dangerous, we have to examine the medium between stars. A single grain of dust, drifting invisibly between the stars, becomes a bullet at high speed. Multiply that by billions of particles along a light-year path, and the emptiness of space begins to look less forgiving. So what exactly fills the gap between stars? Interstellar space is often described as a vacuum. That is mostly true, but not perfectly. On average, the interstellar medium contains about 1 atom per cubic centimetre. That density is far thinner than any vacuum we create in laboratories. In ultra-high vacuum chambers on Earth, we might achieve densities of a few million particles per cubic centimetre. Interstellar space is orders of magnitude emptier. But velocity changes perspective. At 10% of light speed, roughly 30,000 kilometers per second, even a lone hydrogen atom striking a spacecraft carries significant kinetic energy relative to the hull. The energy per particle scales with velocity squared in classical terms, and relativistically at higher speeds. Over years of travel, the cumulative effect becomes radiation exposure and material erosion. We know the density of the interstellar medium through multiple methods. Radio telescopes detect the 21 centimeter emission line of neutral hydrogen. That spectral line arises from a hyperfine transition in hydrogen atoms. By mapping its intensity across the sky, astronomers infer gas distribution. Spacecraft like Voyager have also measured particle densities directly as they cross the heliopause into interstellar space. Plasma instruments recorded changes in charged particle populations. The data converge. Interstellar space is sparse but not empty. Now consider dust grains. These are microscopic particles composed of silicates, carbon compounds, and ice. Infrared observations reveal their presence because dust absorbs starlight and re-emits it at longer wavelengths. Spectral features indicate composition. Extinction curves show how starlight dims and reddens as it passes through dust clouds. Most grains are tiny, often less than a micrometer across, but occasionally, larger grains exist. Even a grain weighing a microgram, impacting at 20% of light speed, would release energy comparable to detonating several kilograms of conventional explosive. In a materials lab, a high-velocity impact gun fires small projectiles into test samples. The chamber echoes with a sharp metallic crack. Sensors record stress waves. The damage spreads in a spiderweb pattern. At relativistic speeds, conventional impact experiments cannot fully replicate conditions, but scaling laws help estimate outcomes. Here is the mid-course reframe. Shielding solves part of the problem, but shielding adds mass. If we add a thick layer of protective material at the front of the spacecraft, we increase total mass. Increased mass demands more propulsion energy. More energy requires larger power systems. Larger systems add more mass. The cycle is relentless. One proposed solution is a layered shield. The first layer, perhaps a thin sacrificial plate, vaporizes incoming particles. Behind it, a gap allows debris to disperse before striking a secondary shield. Whipple shields already protect satellites from micrometeoroids in Earth orbit. Their effectiveness is measured in laboratory tests and on-orbit performance. But those satellites move at about 8 kilometers per second. Interstellar probes at tens of thousands of kilometers per second would face impacts millions of times more energetic per particle. Material science would need to advance accordingly. Magnetic shielding is another concept. If a spacecraft generates a strong magnetic field ahead of it, charged particles could be deflected. This works for solar wind particles, which are ionized. It does not work for neutral dust grains. Some proposals suggest ionizing incoming material with a laser before deflecting it magnetically. Each step adds complexity and energy demand. In a conceptual rendering room, engineers project a glowing magnetic bubble in front of a sleek craft. The projection flickers softly. A low electronic hum accompanies the animation. The bubble bends particle trajectories in elegant arcs. On paper, it works. In practice, It demands field strengths and power supplies far beyond current spacecraft capabilities. Radiation is another hazard. At high velocities, the interstellar medium effectively becomes a headwind of high-energy particles for crewed missions. Shielding against ionizing radiation is already a major challenge within our own solar system. Galactic cosmic rays pose risks to astronauts beyond Earth's magnetosphere. Add relativistic motion, and the flux increases dramatically in the forward direction due to relativistic beaming. Detectors on satellites measure cosmic ray flux regularly. They record spikes during solar storms and steady backgrounds from distant supernova remnants. These measurements inform models of radiation exposure. The models are not speculative. They're grounded in observed particle counts and energies. 1 light-year of exposure at high speed would require shielding strategies far more robust than those used in low Earth orbit. Water, polyethylene, and advanced composites are candidates. Each kilogram adds to launch mass. Again, the loop tightens. In a quiet underground lab, radiation detectors click softly as background counts register. A monitor displays dose rates in real time. Scale those numbers up to years at relativistic speed, and the biological implications become stark. So interstellar travel is not merely a matter of going fast. It is a matter of surviving the journey through a medium that becomes increasingly hostile as speed rises. Yet this does not make 1 light-year unreachable. It defines engineering targets. If we know particle density, we can calculate expected impact rates. If we know dust size distribution from infrared surveys, we can model worst-case scenarios. If we test materials under extreme conditions, we can refine designs. The universe provides data. We must interpret it carefully. There is another subtle factor: navigation. At high speed, even small trajectory errors magnify over years. Stars move. The galaxy rotates. Gravitational influences accumulate. Crossing 1 light-year is not like crossing a static field. It is threading a path through a dynamic system. In a planetarium dome after closing hours, projected stars drift slowly across the ceiling. The motion is accelerated to show thousands of years in minutes. A faint ventilation system hums in the background. Patterns shift. Constellations distort. The sky is not frozen. If we launch today toward a target 1 light-year away, we must account for its proper motion and radial velocity. Those are measured through parallax and Doppler shift. Spectrographs reveal how spectral lines shift toward blue or red, indicating motion toward or away from us. Combine that with angular motion across the sky, and we predict future positions. Precision matters. Because at relativistic speeds, even a tiny angular miscalculation could mean missing a destination by millions of kilometers. Autonomous navigation systems would need to adjust course using onboard star trackers and gyroscopes, cross-referencing survey maps of the sky. Every solution introduces new constraints. 1 light-year is not just distance. It is environment, motion, radiation, and time woven together. If we could solve propulsion and shielding, if we could navigate precisely and sustain power for years, another question emerges. How would we communicate across that gulf? How would we know the mission is alive, progressing, or arrived? Because even if the ship makes it, information cannot outrun light. And that brings us back to the fundamental link between distance and time that defines a light year in the first place. A signal leaves a spacecraft and cannot arrive any faster than light allows. No matter how advanced the engine, no matter how bold the mission, information is chained to that same cosmic limit. So even if we cross 1 light year, how do we stay connected? Communication is distance measured in delay. When Voyager 1 transmits a signal today, it takes more than 22 hours to reach Earth. Engineers calculate that delay precisely using the known speed of light and the measured distance from radio telemetry. The Deep Space Network sends a command. The probe responds almost a day later. Every instruction is patient. Scale that to 1 light year. A message sent from a spacecraft exactly 1 light year away would take 1 full year to arrive. A reply would take another year. The round-trip time is 2 years. Real-time control becomes impossible. We already understand this limitation through daily operations in the solar system. Mars rovers experience communication delays ranging from a few minutes to over 20 minutes, depending on planetary alignment. Commands are sequenced carefully. Autonomy is built into onboard systems. The delay is not theoretical, it is measured in every packet timestamp. For an interstellar mission, autonomy becomes absolute. In a quiet control center at night, rows of monitors glow faintly. A clock displays coordinated universal time. Engineers watch a countdown to signal reception. When the data finally arrives, a soft confirmation tone sounds. That tone represents photons that have crossed billions of kilometers without error. 1 light-year multiplies that experience. Power required to transmit over 100 kilometers is 100 kilowatts. Power required to transmit over interstellar distances is significant, but manageable for small probes. The signal weakens with distance according to the inverse square law. Double the distance and intensity drops by a factor of 4. At 1 light-year, the received signal would be extremely faint. Sensitive receivers and large dish antennas would be required. We already build such systems. Radio telescopes detect emissions from distant pulsars thousands of light-years away. The principle is sound. But communication delay introduces a conceptual shift. Midway through our reasoning, we recognize that travel time and communication time are intertwined but distinct. A probe traveling at 10% of light speed would take 10 years to cross 1 light-year, yet any update about its arrival would reach Earth 1 year after the event. For observers on Earth, confirmation of success always lags behind reality. There is no workaround. Laser communication offers higher data rates. Instead of radio waves, tightly collimated optical beams carry information. Experiments between satellites and ground stations have demonstrated high bandwidth optical links. Atomic clocks synchronize transmission windows. Adaptive optics compensate for atmospheric distortion. Yet even laser beams obey the same speed limit. They cannot arrive sooner. Picture a mountaintop observatory at night. A telescope dome opens with a low mechanical groan. A faint green laser beam extends into the sky for calibration. Inside, detectors wait for photons from a distant spacecraft. The room is silent except for cooling fans. Each photon that strikes the sensor has traveled across space at an immutable speed. Communication is also about pointing accuracy. Over 1 light-year, even a tiny angular error spreads a beam across enormous area. To hit Earth with a narrow laser beam, a spacecraft must know our planet's future position precisely. Earth orbits the Sun. The Sun orbits the galactic center. Predicting position years in advance requires detailed models. Those models are grounded in celestial mechanics, tested by centuries of astronomical observation. Ephemerides tables, refined by radar ranging to planets and laser ranging to the Moon, provide accurate predictions. Lunar laser ranging experiments, where lasers are fired at retroreflectors left by Apollo missions, measure Earth-Moon distance to within centimeters. The round-trip time of photons is recorded with atomic clocks. This is how we verify orbital dynamics. The same mathematics scales outward. So communication across 1 light-year is feasible in principle. It is slow, but not impossible. The limitation is fundamental. Information cannot outrun light. This leads to a deeper reflection. Even if we build a ship capable of crossing 1 light-year in 10 years, from Earth's perspective we would wait 11 years to receive confirmation of arrival. If the ship travels faster, closer to light speed, time dilation might reduce onboard travel time, but Earth still waits at least 1 year for the signal. Distance enforces patience. In a dim office lit by a single desk lamp, a scientist studies a timeline chart. Coloured bars represent travel phases. Thin lines mark communication delays. A faint ticking clock on the wall measures seconds that feel trivial compared to years of silence between messages. There is another complication. Power generation for communication systems must last for decades. Radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity, power Voyager. Their output decreases gradually as isotopes decay. Engineers account for this by managing instrument loads carefully. For an interstellar probe, long-lived power sources would be essential. Nuclear reactors or advanced batteries could supplement radioisotope systems. Each adds mass. Each demands shielding and heat rejection. The pattern repeats. Propulsion, shielding, navigation, communication. Every subsystem feeds into the next. 1 light-year is not conquered by a single breakthrough. It is addressed by an ecosystem of technologies working in harmony within strict physical limits. So far, we have focused on robotic probes. But what if we imagine humans making the journey? If travel times stretch to decades or centuries at achievable speeds, biology becomes part of the equation. Life support, generational continuity, psychological resilience. These are not mere science fiction concerns. They are measurable constraints tied to closed ecological systems and human lifespan statistics. The question shifts from kilometers and joules to years and generations. If we cannot outrun light, and if energy demands cap our speed, then perhaps we must rethink not only how we travel, but who travels. To explore that possibility, we have to examine the limits of human time against the scale of a light year. A child is born aboard a ship that will never see its destination. That idea feels distant, almost mythic. Yet if crossing 1 light year takes centuries at attainable speeds, human time becomes the limiting resource. So what happens when biology replaces propulsion as the clock? At Voyager's speed, 18,000 years per light year, no human crew could survive the journey. Even at 190 kilometers per second, the record set by Parker Solar Probe, 1,500 years would pass. Those spans exceed recorded civilization. So proposals shift toward generation ships. A generation ship would travel slowly, perhaps at a few % of light speed, with a self-sustaining human population living and reproducing on board. If the cruise speed were 1% of light speed, about 3,000 kilometers per second, 1 light year would take 100 years. That is within the scale of multiple generations. But sustaining life for a century in isolation demands closed ecological systems. We have tested pieces of this concept. Biosphere experiments on Earth attempted to create sealed environments where plants, microorganisms, and humans coexist. Results showed how delicate such systems are. Oxygen levels fluctuated. Microbial populations shifted unexpectedly. Even on Earth, maintaining balance proved difficult. On the International Space Station, astronauts rely on recycling systems that reclaim water from humidity and waste. Air is scrubbed of carbon dioxide using chemical absorbers. These systems are monitored constantly. Failures are corrected quickly with resupply from Earth. A generation ship would have no resupply. In a greenhouse module lit by soft artificial sunlight, leaves rustle gently under circulating air. Water trickles through hydroponic channels with a quiet flow. Sensors measure humidity and carbon dioxide levels in real time. Each reading represents survival margins. Population dynamics add complexity. To maintain genetic diversity over many generations, a minimum population size is required. Studies in population genetics suggest that hundreds, perhaps thousands, of individuals would reduce the risk of inbreeding depression over centuries. That increases ship mass dramatically, living space, food production area, and radiation shielding scale with population. Radiation remains a concern even at modest speeds. Galactic cosmic rays penetrate shielding over long durations. Epidemiological data from astronauts and radiation workers provide partial insight into long-term risks. But century-long exposure in deep space has no direct precedent. Models extrapolate from known dose-response relationships. Uncertainty remains. Here is the mid-course reframe. Even if life support and genetics are solved, social stability becomes critical. Human societies are dynamic. Cultural drift, conflict, resource allocation disputes. Over generations, the original mission intent could erode. Governance structures would need resilience across timescales rarely tested in isolated communities. In a rotating habitat concept, a massive ring spins slowly to create artificial gravity. The structure hums faintly as bearings turn. Children run along curved corridors under simulated gravity. Outside the windows, stars remain fixed and distant. The destination is an abstraction decades away. Rotation introduces engineering demands. To generate Earth-like gravity at the rim, the habitat must spin at a specific rate depending on radius. Too small a radius and rotation causes discomfort due to Coriolis forces. Large radii increase structural mass. Structural mass increases propulsion energy requirements. Again, mass feeds back into energy. Some propose suspended animation as an alternative. If humans could enter a state of metabolic stasis, Travel time from the crew's perspective would shrink psychologically. Cryogenic preservation research explores lowering body temperature to reduce metabolic demand. Certain organisms on Earth, like tardigrades, survive extreme conditions by entering dormant states. However, human cryopreservation at the organism level has not been demonstrated with revival after deep freezing. Cells can be preserved. Organs face challenges due to ice crystal formation and biochemical damage. Research into vitrification, which avoids ice crystal formation by turning fluids into glass-like states, shows promise for tissues. Whole human revival remains speculative. Experiments are measurable. Cryoprotectants are tested. Organ viability is assessed after thawing. Progress is incremental. There is no hidden success waiting quietly. Even if suspended animation became feasible, propulsion energy and shielding constraints would remain. The ship still must endure decades or centuries in transit. Another approach leverages relativity itself. If a crewed ship could reach very high fractions of light speed, time dilation would reduce onboard travel time. At 99% of light speed, a 1 light-year journey might take just over 1 year on board, while more than 7 years pass on Earth. That shrinks subjective travel time without altering Earth's weight. But reaching 99% of light speed requires the extreme energies we calculated earlier. For large crewed vessels, the energy demand approaches a significant fraction of global annual production. Infrastructure would need to scale enormously. In a vast orbital construction yard, imagined high above Earth, skeletal frameworks of a starship extend against the blackness. Welding arcs flash briefly with sharp white light. A low vibration resonates through the structure as modules lock into place. The scale dwarfs anything humanity has yet built in space. So the human question circles back to propulsion and energy. 1 light-year is not just a technical challenge, it is a generational commitment unless velocity climbs close to light speed. Even then, communication delay ensures that Earth and travelers diverge in time experience. Families separated by relativistic journeys would age differently. Atomic clock experiments confirm this divergence at small scales. In laboratories, synchronized clocks placed at different altitudes tick at measurably different rates due to gravitational time dilation predicted by general relativity. GPS satellites adjust for both special and general relativistic effects to maintain navigation accuracy. Without these corrections, positioning errors would grow by kilometers per day. Time is not uniform, we measure its variation daily. So when we contemplate a human journey of 1 light-year, we are not speculating about exotic physics. We are extrapolating from clocks already corrected for relativistic drift and spacecraft, already tracked across billions of kilometers. The constraints are familiar, just amplified. In a quiet habitation module, lights dim to simulate night. A soft ventilation system hums. Outside, the stars remain cold and unblinking. Inside, generations live and die. The destination remains 1 light-year away, slowly approaching. If slow travel strains biology and fast travel strains energy budgets, some ask a more radical question. What if we do not move through space in the usual way at all? What if we attempt to bend space itself? That idea leads us to the most speculative but mathematically grounded proposals in modern theoretical physics. And to examine them responsibly, we must separate what equations allow from what reality is confirmed. A diagram on a chalkboard shows space compressed in front of a ship and expanded behind it. The ship itself never moves faster than light locally. Space does the moving. It sounds like a loophole in the cosmic rulebook. So can we bend our way across 1 light-year? The idea is often called a warp drive. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's field equations of general relativity that allowed for a warp bubble. Inside the bubble, a region of flat spacetime would carry a spacecraft. Space ahead would contract. Space behind would expand. From the perspective of distant observers, the bubble could move faster than light without locally violating relativity. The key phrase is solution to the equations. Einstein's equations relate mass energy to the curvature of spacetime. They have been tested repeatedly. Gravitational lensing, where light from distant galaxies bends around massive clusters, matches predictions. The precession of Mercury's orbit deviates from Newtonian expectations in exactly the way general relativity predicts. Gravitational waves, detected by the laser interferometer, Gravitational Wave Observatory, confirmed ripples in spacetime from merging black holes. The mathematics is not fantasy, it is verified. But the Alcubierre solution requires something extraordinary: negative energy density. In classical physics, energy density is positive. Matter has positive mass energy. Even radiation carries positive energy. The warp metric demands regions of spacetime with negative energy to create the contraction and expansion pattern. Quantum field theory does allow small negative energy densities in certain configurations, such as the Casimir effect. When two conducting plates are placed extremely close together in vacuum, quantum fluctuations between them are restricted, producing a measurable attractive force. This effect can be calculated and has been measured in laboratories with high precision. However, the magnitude of negative energy in the Casimir effect is tiny. To generate a macroscopic warp bubble large enough for a spacecraft, early calculations suggested energy requirements comparable to the mass energy of a planet or more. Later refinements reduced the estimate but still required amounts far beyond anything humanity can produce. Moreover, sustaining such a configuration without instability remains unresolved. Here is the mid-course reframe. Even if negative energy could be generated in sufficient quantity, there are additional constraints. Some analyses indicate that a warp bubble might produce intense radiation at its front edge, potentially destructive to both the spacecraft and anything at the destination. Other studies suggest that controlling the bubble's formation and collapse would require pre-existing manipulation of spacetime along the path. These are not settled conclusions, they are active areas of theoretical investigation. The key point is that no experiment has demonstrated macroscopic spacetime manipulation of this kind. There is no hidden prototype. In a quiet theoretical physics office, papers lie scattered across a desk, equations curve across pages in careful handwriting. Outside the window, evening light fades. A faint rustle of paper accompanies each page turn. The work is abstract, but it rests on equations already validated by observation. Another concept involves traversable wormholes. In principle, a wormhole would connect two distant regions of spacetime through a shortcut, enter one mouth, and emerge near a distant star. Solutions to Einstein's equations permit such structures under certain conditions. Again, exotic matter with negative energy density appears necessary to stabilize the throat of a wormhole. Without it, the tunnel would collapse too quickly for passage. Observationally, we have no evidence of naturally occurring traversable wormholes. Gravitational lensing surveys have not revealed signatures consistent with stable macroscopic wormholes. We must be careful here. General relativity allows mathematically consistent geometries that our universe may not realize physically. The existence of a solution does not guarantee the existence of the structure. Observations constrain what kinds of stress energy distributions occur in nature. So far, none resemble the sustained negative energy densities required for warp travel. Quantum gravity, a still incomplete theory unifying general relativity and quantum mechanics, might offer new insights. But as of now, no experimentally confirmed framework provides a practical mechanism for faster-than-light travel. So the ceiling remains: 1 light-year cannot be crossed faster than light in our current understanding of physics. Space can expand between galaxies at effective rates exceeding light speed because it is space-time itself stretching, not objects moving through space. But harnessing that expansion locally for transport is beyond demonstrated science. In a planetarium darkened to simulate deep space, a projection shows galaxies drifting apart over billions of years. A soft, ambient tone fills the dome. The expansion is subtle, relentless, measured through redshift. Spectrographs on Earth detect the stretching of spectral lines. From that, we infer cosmic expansion. Redshift is how we know the universe is expanding. It is not speculation. It is measured shift in wavelength compared to laboratory references. If expansion can separate galaxies faster than light, why can we not ride that expansion? Because the expansion is uniform on large scales and governed by cosmic dynamics. Local regions like galaxies remain gravitationally bound. Engineering spacetime on demand would require control over energy densities far beyond our reach. The idea is intoxicating. The constraints are sobering. So when we ask how long it would take to travel 1 light-year, Warp drives and wormholes offer no currently testable shortcut. They remain theoretical possibilities bounded by extreme requirements and unverified physics. That returns us to the grounded options. Relativistic travel at significant fractions of light speed appears physically possible but energetically expensive. Slow travel with generation ships is biologically complex but does not violate physics. Robotic probes propelled by beamed sails may achieve interstellar crossings within decades. All of these paths respect the speed limit, none erase it. In a quiet observatory control room, a star's spectrum appears on a monitor as thin, dark lines against a rainbow band. A soft electronic hum underscores the steady acquisition of data. Each line tells us composition and motion. Each measurement ties us back to the same constants. 1 light-year remains 9.5 trillion kilometers. The speed of light remains fixed. The equations hold. If faster than light travel lies beyond current science, then perhaps the most realistic near-term goal is not crossing vast distances with humans, but sending fast, lightweight probes to the nearest stars. That raises a practical question. If we chose the closest realistic target, using measured distances and known stellar properties, how long would it actually take under different propulsion assumptions? To answer that, we must focus on a specific star and run the numbers carefully, without exaggeration or despair. A faint red star flickers in the southern sky. It is closer to us than any other star beyond the Sun. If we cannot reach it, then 1 light-year remains abstract. So let us choose a real destination and measure the journey honestly. That star is Proxima Centauri. Proxima Centauri lies about 4.24 light-years away from Earth. That distance is not a guess. It is measured primarily through parallax. As Earth orbits the Sun, Proxima's apparent position shifts slightly against more distant background stars. Space observatories like Gaia measure that shift with extraordinary precision down to microarc seconds. From that tiny angle and the known radius of Earth's orbit, geometry yields distance. 4.24 light-years. Proxima is a red dwarf, much smaller and dimmer than our Sun. Spectral analysis reveals strong molecular absorption bands typical of cool M-type stars. Its radial velocity, measured through Doppler shifts of spectral lines, tells us it is moving slowly relative to the Sun. Proper motion measurements show its gradual drift across the sky. It is not standing still. Now let us run scenarios. If we sent a Voyager-class probe travelling at 17 kilometers per second, the journey to Proxima would take roughly 75,000 years. That is simply 4.24 light-years multiplied by 18,000 years per light-year. No rounding trick rescues it. If we could sustain Parker Solar Probe's peak speed of 190 kilometers per second in interstellar cruise, which it cannot currently do, the trip would take about 6,000 years. These are baseline realities. Now consider a more ambitious but still sub-relativistic speed. Suppose we achieve 1% of light speed, about 3,000 kilometers per second. That is nearly 15 times faster than Parker's peak. At 1%, 1 light-year takes 100 years. So Proxima would require about 424 years of travel, plus acceleration and deceleration. 4 centuries. That places arrival in a future beyond any living memory. If we push to 10% of light speed, 30,000 kilometers per second, 1 light-year takes 10 years. Proxima would be reachable in roughly 42 years of cruise. Add perhaps a few years for acceleration and braking, a half-century mission. This is within a human lifetime. At 20% of light speed, the cruise time drops to about 21 years. At 50%, about 8.5 years. At 90%, roughly 4.7 years in Earth's frame. But here the relativity we discussed earlier returns. At 90% of light speed, gamma is about 2.3. That means time on board would pass more slowly relative to Earth. A 4.7-year Earth frame journey might feel like about 2 years on board. Push closer to light speed, and onboard time shrinks further. Yet Earth always waits at least 4.24 years for any signal sent from Proxima. Communication delay remains fixed by distance. In a simulation lab, a digital star map displays Earth on one side and Proxima on the other. A thin line traces a trajectory. A small timer counts upward in years. The room is quiet except for the low hum of computers. The numbers change smoothly as velocity sliders move. Now comes the mid-course reframe. Reaching 10% of light speed with a lightweight robotic probe using a beamed laser sail might be within the realm of large-scale engineering. For a gram-scale payload, the energy requirement is immense but concentrated over minutes. Infrastructure on Earth or in orbit would provide the power. The probe would not carry fuel for acceleration. However, decelerating at Proxima is difficult. Without a powerful laser stationed there, the probe would likely fly past the system at high speed, collecting data in hours or days. That limits scientific return. If instead we attempt to decelerate using onboard propulsion, we must carry fuel, increasing mass and energy needs. Alternatively, magnetic sails interacting with Proxima's stellar wind could provide gradual braking, but this remains theoretical and untested at scale. For a crewed mission at 10% of light speed, energy and shielding demands multiply. If the spacecraft mass were 1,000 tons, accelerating and decelerating would require energy comparable to a meaningful fraction of annual global consumption. As we calculated earlier, infrastructure would need to be built in space, likely using resources from asteroids or the Moon to avoid Earth's gravity well. Launching such a project is not only a physics challenge but an economic and political one. In a conceptual orbital yard, trusses extend like skeletal ribs against Earth's curve below. Welding sparks flash briefly, then fade. A distant thruster test emits a muted roar that vibrates through the structure. Construction in microgravity allows larger assemblies than on Earth, yet every component must still obey material limits measured in tensile strength and thermal tolerance. Proxima itself hosts at least one confirmed exoplanet, Proxima b, detected through radial velocity measurements. Astronomers observed periodic shifts in the star's spectral lines caused by the gravitational tug of an orbiting planet. The amplitude of the Doppler shift, measured in meters per second, reveals minimum planetary mass. The orbital period is about 11 days. These are real, measured numbers. Proxima b lies within the star's habitable zone, where temperatures might allow liquid water under suitable atmospheric conditions. That possibility fuels interstellar ambition. Yet Proxima is a flare star. It emits frequent bursts of high-energy radiation. Observations from space telescopes detect these flares in ultraviolet and X-ray bands. Any planet there faces harsh space weather. So our destination is not a serene twin of Earth. It is a challenging environment. 1 light-year is the unit that shapes all these considerations. 4.24 of them define the nearest target. If we accept 10% of light speed as a plausible future benchmark for robotic probes, then reaching Proxima within half a century becomes conceivable in principle. For crewed missions, the same speed demands transformative energy infrastructure and shielding solutions. The hard constraint remains. Nothing we have measured suggests we can exceed light speed. Atomic clocks, particle accelerators, redshift surveys, and laser ranging all reinforce the same constant. The speed of light is not a technological limitation. It is woven into space-time. In a quiet outdoor setting far from city lights, the night sky stretches overhead. Proxima is too faint to see with the naked eye, but Alpha Centauri shines nearby. A gentle wind moves through grass with a soft whisper. We look up and see stars as they were years ago. The light is delayed. Distance is time. So how long would it take us to travel 1 light-year with current technology? Thousands to tens of thousands of years. With advanced but physically plausible propulsion. Perhaps decades for small probes. Perhaps centuries for large crewed vessels. With speculative space-time engineering, unknown and unproven. But to truly answer the question, we must step back. Because 1 light-year is not just a travel problem. It is a lesson about limits, measurement, and perspective. And to understand what that lesson means for us, we need to gather the threads we have followed and see the larger pattern they form. A year of light is a measure of patience. It is a number that seems small on a cosmic map and immense against a human life. Tonight, we've traced that number from laboratory clocks to distant stars, and it has refused to bend. A light year is about 9.5 trillion kilometers. The speed of light is about 300,000 kilometers per second. Those two anchors define the scale. One sets the distance, the other sets the limit. We began with a simple question. How long would it take us to travel 1 light-year? With chemical rockets like those that launched Voyager, the answer is measured in tens of thousands of years. With the fastest speeds ever achieved by a human-made object, it is still more than a millennium. With ambitious but physically grounded concepts like laser-driven sails, a lightweight probe might cross that gulf in about 5 to 10 years at significant fractions of light speed. For crewed missions at similar speeds, the energy and shielding demands rise to levels that would require a civilization-scale commitment. Why does this framing exist? Because our intuition evolved on a planet where the horizon is a few kilometers away and the sun is 8 light minutes distant. We think in hours and miles. A light year exposes the failure of that intuition. It forces us to translate distance into time and time into energy. Zoom out slowly. From a car on a highway, distance is fuel and patience. From a rocket leaving Earth, distance is delta V and propellant mass. From a relativistic spacecraft, distance becomes gamma factors and joules measured against global energy budgets. From a cosmological perspective, distance is redshift and expansion measured by spectral lines stretching across billions of years. Each step expands the scale. We know these numbers not by imagination but by measurement. Parallax shifts measured in microarc seconds fix stellar distances. Atomic clocks and laser pulses define the meter itself. Radio telemetry and Doppler tracking reveal spacecraft velocity. Particle accelerators confirm the energy cost of approaching light speed. Spectrographs measure redshift and stellar motion. Survey mapping projects chart the drift of stars across the galaxy. Tie distance to time. When we look at Proxima Centauri, we see it as it was 4.24 years ago. That delay is not metaphorical. It is the travel time of photons through vacuum. When Voyager sends a signal, we wait nearly a day because light must cross billions of kilometers. Communication lag is simply distance expressed in seconds and years. The hard constraint remains unchanged. No object with mass has been observed to reach or exceed the speed of light. The equations of relativity predict infinite energy would be required. Experiments in accelerators confirm that as particles gain energy, their velocity approaches but never attains that limit. Every clock experiment, every laser ranging test, every redshift measurement reinforces the same structure of spacetime. This is not a wall built to frustrate us. It is a property of reality. And yet within that constraint there is room for wonder. We are small compared to a light year. A human life spans perhaps 80 years. 1 light year at 1% of light speed is a century of travel. We cannot casually stroll between stars, but we have already sent machines beyond the heliosphere. We have measured the expansion of the universe. We have detected planets orbiting other suns by tracking spectral lines that shift by meters per second. We are made of stars, once. The iron in our blood and the carbon in our cells were forged in ancient stellar cores. The same physics that limits our speed also allowed those elements to form. The laws that constrain us are the laws that created us. Next time you see the night sky, remember this. Every star you see is separated from you by years of light travel. You're looking into the past. The darkness between those points is not empty in the poetic sense. It is structured by constants measured in laboratories and verified by satellites. If we ever cross 1 light year with human passengers, it will not be because the universe changed its rules. It will be because we learned to work within them at unprecedented scale. Before we close, consider this quietly. The question was not only about travel time, it was about understanding what distance truly means. 1 light year is not just far. It is a reminder that space and time are intertwined, that energy is finite, and that ambition must negotiate with physics. Good night. And when you look up, let the silence between the stars feel less like emptiness and more like a measured, luminous span of time.